Good afternoon, dear honorable guests, students, ladies and gentlemen. Welcome back to the International Conference on Mathematics, Statistics, and Data Science 2020, so-called ICMSDS 2020. We now come to the panel session 2. Two honorable speakers will share with us on this beautiful afternoon. Professor Ken Seng Tan from Nanyang Technology University of Singapore and Professor Muhammad Hisham Lee from University Technology of Malaysia. And the panel session 2 will lead by Ms. Tuti Purwaningsi MSI from Universitas Islam Indonesia. Ladies and gentlemen, allow me to read her curriculum vitae in advance. Tuti Purwaningsi MSI, lecturer at the Department of Statistics, Universitas Islam Indonesia. Her academic background, Master of Statistics from IPB University the year 2014. Her research interest is at the area of information technology and big data. And by the year 2020, she received award as a trainer of international certification specialist data visualization. Ladies and gentlemen, let us together welcome Dr. Tuti Purwaningsi. Miss Tuti.
Hello, Miss Sarah.
The time is yours.
Okay, thank you, Miss Sarah. Okay, good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you for still here in the plenary session with our prestigious speakers today in International Conference on Mathematics.
Ms. Tuti, please unmute your speaker first.
I already unmute my speakers. Okay. Okay.
Okay, thank you. We can hear your voice. Thank you. And the time is yours to lead this panel session.
Okay, thank you, Miss Sarah. Okay, assalamualaikum warahmatullahi wabarakatuh.
You're most welcome.
Good afternoon, ladies and gentlemen. Thank you for still here in plenary session with our prestigious speakers today in International Conference on Mathematics, Statistics, and Data Science 2020. And in this session, we will have two great speakers from Singapore and Malaysia. This session will have 30 minutes for every speakers and continue to Q&A session about 11 minutes. And the first speaker is from Nanyang Technological University, Professor Ken Seng Tan. Hello, Professor. I'm Tuti.
Hi, everyone.
Hello. I know you from one of my lecturer, Ibu Dian Kusumaningrum. I think she is here and you got greeting from her. Okay. I will read the CV of Prof. Ken. Prof. Ken is a professor of actuarial science. And the deputy in the Division of Banking and Finance, Nanyang Business School, and director of the Insurance Risk and Finance Research Center, Nanyang Technological University. And Professor Ken is very active in conducting research, reforming education, and strengthening the profession. Professor Ken's research interest is about intersection of actuarial science, insurance, finance, mathematics, and statistics. Prof. Ken is the co-editor of North American Actuarial Journal and the associate editor of the Annals of Actuarial Science and Agriculture Finance Review. Professor Ken also received many awards there, including the Reddington Prize and then the NAAJ annual prizes and also many awards there. And in this session, Prof. Ken will share his research about improved index insurance design and yield estimation using a dynamic factor forecasting approach. Please, Professor Ken, time is yours.
Right. Can I share screen then?
Yes.
Okay, so are you able to see my slides?
Yes, we able to see your slide.
Okay, perfect.
Okay.
First of all, thank you to Ibu Tuti for the introduction. It's really a great pleasure and a great honor to be here. And also thank you to Ibu Anissa for the invitation for this special conference. And indeed, this is a very exciting, very timing conference on mathematics, statistics, and data science. Okay, so my talk today is on improved index insurance design and yield estimation using a dynamic factor forecasting approach. The theme of this is quite timely in a sense that it does rely on a lot of data, and talking about how best exploit the data that we have, and particularly by applying to insurance, application, or, more specifically in the agriculture area. So that's sort of the main premise of this presentation. And this work is actually a joint work with, Hong Li, Lisa Porch. They're both at University of Manitoba, Canada. And my colleague, Wenjin Zhu, she's also a, lecturer at the Nanyang Technological University. And again, great news to share as well. In fact, just over the weekend, this paper was just accepted in insurance, mathematics, and economics. So great news, okay. This project is actually supported by the Society of Actuaries Center of Actuarial Excellence Grant Program on maintaining financial stability in an era of changing climate and demographics. Okay. So without further ado, so the key highlights in this paper, basically there are three parts. One is talk about, our proposed so-called dynamic factor yield forecasting approach. So this is where we propose a new model for, forecasting crop yield. And after we have that, then we talk about how to enhance the index-based insurance policy by exploiting this particular, dynamic factor model that we are proposing in this paper. And finally, we will conclude the paper with some empirical evidence, supporting evidence. So introduction. So again, why do we care about, yield forecasting, right? Why do we work so hard at getting a model which will be very accurate? And again, from the farmer's perspective, if you have a good yield casting model, then you will be able to predict with a high degree of confidence, what will be the crop production at the end of the year or at the end of the harvest season. So in this case, you can make a more preparation in terms of the crop sales or even the marketing and so on. And also depending on the outcome, this will also enhance your risk management practices, right? Whether, for example, typically for crop insurance, you may have to make a decision at the beginning of the season to whether you should buy an insurance or not. So if you have a good, credible crop yield model, this will potentially, provide, this kind of information. And from the insurer or especially the government perspective, so certainly if you have a very effective model, then it can provide a more effective and more sustainable rate making, especially, for example, if the government or the insurance company are issuing this kind of agriculture insurance policy. So a credible model for pricing this kind of product obviously is very, very important. And also, formation of a more informed policy and innovative risk management approaches that can protect producers from potentially disastrous outcome due to extreme adverse weather. So this is particularly very important in view of the climate change and so on. And finally, that and again also one of the main message in this paper is how to exploit this information if you have a very accurate yield forecasting model, and how to use that to construct an index-based insurance. So in terms of the crop yield modeling approaches, obviously there are a number of different approaches. So let me just broadly classify, for example, the so-called process-based. So again, by process-based, basically, it based on mathematical or typically computer-based representation of one or several processes characterizing the functioning of a well-delimited biological system of fundamental or economical interest. So, and typically, in terms of the crop yield, so you may go into finding out more about, what is the crop management, what is the planting dates, phenology, and what other factors will affect the growth and so on. So, and again, there are a number of literature, work that has been done using this so-called process-based. But what is more relevant or more familiar to us, at least in terms of my background, is the so-called statistical-based model, right? So again, from a statistic point of view, that we try to relate or doing some kind of regression analysis or some kind of like modeling, relate the growth or the crop yield to certain explanatory variables. So those variables typically can be, something that is measurable, right? For example, you may look at the temperature, you may look at the precipitation, and so on, right? So essentially, again, it's a very tiny in terms of this conference is obviously is very much data driven, right? Okay, and also that with the advances in technology, so we can also exploit other information like remote sensing, right? Okay, so especially when using the satellite images, when you have a high resolution data, then this can also be, part of your regressor, for example. Having said that, there are a number of challenges with the statistical approach, especially in the context of, agriculture insurance area, right? First is the availability of crop, yield data. So in most crop yield, right? So typically there could be maybe about 2 or 3 or even 4 harvesting seasons a year. So which means in terms of data points, you may just have 2 or 3 data points a year. So if you imagine that even if you follow through the crop yield the historical data over the last or last 10 or 20 years, so the availability data point is actually quite limited. Especially in this, era where we have been talking about how to use, in the era of big data. So this will be very embarrassing to some extent. Furthermore, explanatory variable selection is an issue because there are so many different variables that you can choose from, just by looking at the temperature, for example. So the key then is, which temperature should you be looking at? For example, if you grow paddy or grow rice or corn or whatever, so it's over the growing season, it could be over several months. So then ask yourself, if you want to choose some explanatory variables, which should you be looking at the daily temperature or should you be looking at the monthly, right? Okay, and so on. So that could be, by itself is another challenging issue as well. All right, again, this model, again, there are a number of people that have been studied, in dealing with these kind of issues. So in terms of our model specification for our work, so basically we're going to consider 2 types of model specification, right? Okay, and we call it, one is the cross-section specification. So basically it studied the average relationship between crop use and the explanatory variable across multiple locations. So this is particular advantageous because there are some variable which are time invariants, for example, soil, right? So again, soil is an important determinant of the growth of the crop yield. And typically we don't expect that it change a lot over time. So if you have a cross-sectional, specification model, this can be incorporated relatively easily. And obviously, a model which is also very commonly used is the so-called time series specification. And basically it focuses on the dynamic relationship between crop yield and the explanatory variable for a given location, and over time, for example, right? Okay. And again, a given location could be farm or county or states. And in these studies, we focus on data at the level of county and the state level. So in fact, for a particular crop that we're looking at and for a given state, we assume there are N counties and T years of data. So for a time series specification, and again, this is really nothing really fancy. This equation or this regression equation should be very familiar to this sort of audience here. So, you know, for example, on the left, this is more at the county level where we try to do a regression at the county level. And the model on the right is at the state level. So essentially, it does an aggregation of the model on the left, right? Okay. So, and again, here I've consistently used the variable J to represent the dimension of this model. And similarly for a cross-section specification, so, and this is where we, rather than looking at the data over time, so we actually look at it, you know, across, you know, among the county level by averaging over all the, you know, time average of those crop yield, okay, all right? So again, but other than that, you know, it's still a very standard type of like multiple regression type model, right? And again, here we use K as the dimension for this particular model. And to implement both set of model, the challenge is the dimension J in the time series specification and dimension K in the cross-section can be very large, especially when we are dealing with a rather limited data point. So in our work, we actually use a so-called dynamic factor analysis in order to achieve some kind of, you know, dimension reduction. So again, the key idea in this paper is really, you know, talking about how to reduce the dimension. And in this work, we sort of propose two, you know, steps. Step one is that a set of latent factor is estimated through, again, you know, if you think about dimension reduction, typically we always think in terms of PCA, right? Principal component analysis. But in this case here, after we have obtained the PCA, we actually go one step further by looking at the so-called dynamic factor procedure and to select the key factor that are important for yield forecasting. So which means that, you know, we are able to, through this process, we're able to further exploit the dimension reduction. And again, the details is actually in the paper. So I'm just going to describe this at a very high level and without going through any details, all right? So in terms of the data, so we have access to, for example, the weather data from PRISM, so and which provide a monthly average temperature and monthly cumulative precipitation. And we also have the soil data from the USDA Natural Resources Conservation Service. And in this case, we have 56, you know, variable on soil. And in terms of the crops, so we actually look at three types: corn, soybean, and winter wheat. And in fact, the you know, in terms of the crop data, we look at over, you know, from the state of Illinois states in the United States. And the reason why we look at these three types of crops, you know, in like namely the corn, soybean, and winter wheat, is that in the state of Illinois, it basically covers more than 80%. You know, more than 80% of the crop production in Illinois, you know, is actually consists of these three types. So, and for that reason, so this is what we have chosen then. In fact, the diagram on the right, you know, shows the, you know, in terms of the magnitude or the intensity of the production for each of the crop. Okay, for example, on the top left, so if you look at those heavily shaded green, so this implies that, you know, the northern part of the Illinois states, you know, are mostly producing corn, whereas in the southern part, predominantly, you know, they are, you know, the winter wheat and soybean. Okay. And in terms of data, we have the survey data again over 1981 to 2016. So as I say, these are the annual data. So in terms of data point, it's actually very limited. And the table here also shows the growing season for each of these crop type. And again, the reason why this is important is when we look at the weather temperature or the weather variable. So we actually look at the corn or soybean or winter and looking at the monthly temperature over the growing season only. Right. So in terms of the empirical result on yield forecasting, so again, we actually look at three different type of model, right? And for each model, we implemented three specifications. So the cross-section specification and the time series specification at both county and state level, right? So for the optimal factor, this is actually based on our proposed so-called dynamic factor model. And this is applied to a design matrix consists of 116 variables, including 61 weather variables and 55 soil condition variables. So, and based on this, then we apply our proposed idea, the proposed dynamic factor approach in order to determine the number of factors optimally. So in this aspect, we refer, this implementation as the optimal factor into the implementation, which is correspond to our proposed dynamic factor model. And in order to compare our results to the existing, literature, we also look at a very standard, like a regression type model proposed by Lobel and Burke in 2010. So, and basically what they have here is for the time series specs, they have regressors, involving the average temperature over growing season. And they also have the total precipitation over growing season in year T. So which means that for the time series specification, so this become simply a two-dimensional, regression model. And for the cross section, we actually look at, not only the linear regressor, we also look at the square term, right? So that again, slightly more sophisticated. So that become a, basically four-dimensional variable. And again, because of the simplicity, so obviously this model has the advantage of simplicity. It can be applied extremely easily. And not only that, it has the so-called model of parsimony, right? So it has only very few explanatory variable only. So the constraint factor model, which is also a third type of model that we'll look at or we'll compare empirically. So this constraint factor model is actually a variation of our proposed dynamic model, except that rather than optimally select those factors, here we confine our factor only to so that it coincides with the benchmark regression model, right? So that when you do a comparison, both benchmark regression model and the constraint factor model will have exactly the number of dimension, so that they are on the same equal footage in terms of comparison, right? In terms of quantitative measure, so we look at two standard one. So one is the so-called adjusted R-square. So basically this provide information about the in-sample goodness of fits. And the other, we look at the so-called leave-on-out cross-validation root mean square error. So, and that obviously provide an information about how good they are performing in terms of our sample forecasting capability. So this table provide information in terms of the in terms of their performance. So, and again, if you look at the first column where it has a benchmark regression. So, and again, if you, depending on which model they look at, whether look at the county level time series or the state level time series or the county level cross section, and so on. So you can see that, comparing the benchmark to the constraint. So constraint is, performs slightly better, right? But if you compare to the optimal factor, so in terms of the adjusted R-square, it has even higher, adjusted R-square. So again, which is kind of not surprising, when you compare to constraint factor versus the optimal, in a sense that the constraint factor is a suboptimal implementation of our dynamic factor model. So the table on the far right gives you some idea about the dimension reduction. So again, recall that for our dynamic factor model, we begin with 116 variables. So on the and as you can see here, in terms of the dimension, so it can go as low as about 3.4%, 3.4 dimension to as high as about 13 dimension and so on. So again, this illustrates that it does have quite a bit of quite effective at dimension reduction. And a word of just to clarify that if you look at the county level time series model, I also have the minimum optimal dimension and the maximum optimal dimension. And the reason is that for the county level time series model, we actually apply the time series model to each and every single county. All right. So which means that for each county, we have the optimal dynamic factor model, and we also have the optimal R star. So and we repeat this across all the different county, and hence we have this so-called minimum optimal dimension and the maximum optimal dimension, and also the average. All right. So for the out-of-sample forecasting, we compare the basically the cross-validation root mean square error. So and again, basically very similar to the pictures provided by looking at the in-sample goodness of fits using the adjusted R-square. So in this case here, in this root mean square error or the cross-validation root mean square error, so it again shows the the optimal factor outperform the other two, right? So again, with the constraint factor sort of perform in the middle, and the regression model is not as good or the worst among the three, right? But what is impressive, if you look at the optimal factor model, there are even a situation where the root mean square error is actually below 1%, right? For example, for the we have some cases which is 0.9%, and we even have the lowest root mean square error is as small as 0.01%. So obviously that provides an additional evidence on the credibility or the effectiveness of the proposed model. So the last part of this presentation focus on the so-called index-based insurance. So again, a generic crop insurance contract is basically can be given by the equation in the first equation. So where the insurance payout is a function of the area, for example, the crop area that you are insuring, the price of the crop, at the beginning, and at the beginning of the growing season, and the key here is this is the max function, right? Okay, so and the key is the if you look at the max function, K again is a predetermined constant, or typically known as a stride level, right? Okay, and YT is the random variable that relate in some way to the yield of the insured crop, right? So what this means is that when YT, when the realized YT is less than K, which means there will be a positive payout from the insurance contract. If YT is greater than K, then the insurance has no value. There's no payment from the insurance contract. So in terms of the insurance contract or the crop insurance, it depending on how we define the random variable YT. If the YT correspond to the actual yield of the farm or the county and so on, then this is called indemnity based, right? Because it depends exactly on the actual yield of the farm, and sometimes it's called MPCI, multiple peril crop insurance. If the YT is some other reference index, such as the weather variables, and we then use the weather variables to relate to the payouts, then in this case, it's called index-based as opposed to indemnity-based. All right. So for the index-based insurance or IBI, there are a number of advantages. For example, it tends to be a lot more cost-effective. It also has the advantage that it will remove or reduce the moral hazard. But the biggest challenge with IBI contract is the presence of the so-called basis risk. Basis risk is just simply the discrepancy between your actual losses and the payments that you receive from the insurance contract. Again, I will have more to say about that later on. So in our empirical analysis, we actually look at two types of IBI. So for the first type, the YT we actually use is correspond to our proposed dynamic model. All right. Whereas the other type is obtained from the benchmark regression model. And we're going to compare, the effectiveness of this kind of index-based insurance policy based on these two reference indices. So now let's talk about more on the basis risk analysis. Again, because of the presence of the basis risk, again, basis risk is a discrepancy between the actual losses incurred by the farmer and the actual payment received from the insurance contract. So in order to quantify this risk, we look at actually based on the frequency idea and the severity and benchmark against the indemnity-based insurance. For the frequency approach, we look at two types of error. So that should be quite familiar to this audience here. The first type, we simply call it a type 1 error, basically implying that the farmer does not receive an indemnity despite a loss incurred on the farm. Whereas for type 2 error, the farmer received an indemnity despite no loss, right? So again, either of these error, is undesirable, from the contract design point of view, from the sustainability point of view, and also from the coverage protection to the farmer, is also non-desirable. So to better understand this type 1 and type 2 error, let's look at this graphically. Suppose the horizontal axis represents the yield losses incurred, so the actual yield losses incurred by the farmer, and alpha, represents that it's the deductible for the indemnity-based insurance contract. So which means that if the losses incurred on the farm or incurred by the farmer is higher than alpha, right, then there will be indemnity payout from the indemnity-based insurance contract. And suppose now the y-axis is a measure of the reference index, right? So, and again, assuming that in the IBI contract or the index-based insurance, there exists a beta, which is the deductible for the IBI. So which means that as long as the index above beta, then there will be a payment from the IBI contract. All right. So again, very simply in this diagram, if the farmer actual losses is higher than alpha, then there should be a payments, based on the indemnity-based insurance. But if it is a IBI, then if the reference index is higher than beta, then there will be a insurance payouts. So what this means is that the area on the red, so that will be so-called type 1 error. And the type 2 error, again, will be the one in the shaded yellow. And the one in the green, right, representing there's no payout because the actual losses is less than alpha, and the reference index is also less than beta. So which means that both contracts do not produce any insurance payouts. So which means this is an example where we have zero error in terms of type 1 error. And similarly, for the region in the shaded blue, so this is the region where there is an actual payout or there's an actual losses. At the same time, there's also a positive payout from the IBI. So in other words, this is the area where it also has zero type 1 error. But even though it has zero type 1 error, depending on the actual size of the payments or depending on the magnitude of the payment from the IBI compared to the actual size of the indemnity from the indemnity-based insurance contract, there could exist a situation where you could overcompensate it or undercompensate it. So this implies that even though in the region, in the blue region, even though it has zero type 1 error, so this is still not sufficient. We should actually compare in terms of the actual amount, the magnitude of losses or the magnitude of payments. So in this case here, it's a severity, all right? We can look at it by looking at the severity. So this slide, again, compare between the type 1 and type 2 error for different model, right? Again, as you can see, yeah. Okay, I will just take another one or 2 minutes, okay?
Okay. Thank you.
All right. So in terms of this, again, you can see that in the best case, from the dynamic factor model, we actually could produce a type 1 and type 2 error, of 0%. Obviously, that's the most, ideal situation, all right? Compared to the regression, which produces 33.33% and 26.67%. And again, when you compare the mean, so which is in terms of severity, so and you can see that, for example, for the dynamic factor model for corn is 0.33 versus 0.63 and so on. So this slide again shows, let's say if, and this is a, looking at the different county, right? Okay, and look at, for example, the mismatch in terms of the size of the payments. As you can see that on the left-hand side of the left-hand graph, the dynamic factor model is pretty stable, is almost 0. And the variability is also, it fluctuates also with a very small variability. But for the benchmark model, the variation definitely seems to be much higher. And also the mean value seems to deviate quite a lot from 0. So again, these provide another evidence, indicating the robustness of our proposed model. So in conclusion, so this paper investigated a new approach to forecast yield using a dynamic factor model and propose a weather index-based insurance policy based on the proposed forecasting model. A dataset consisting of county level and state level annual crop production in 3 crops are being used in this analysis. And again, empirically, we use a number of empirical results and seems to show that there are some advantages with our proposed model, especially and used to model or in how to design the index-based insurance. So again, thank you very much for your time. On that note, this is where I will stop. And again, I apologize for taking over time. Thank you.
Okay, thank you very much, Prof. Ken. This is a great presentation, this afternoon. And let me to introduce the next speaker, Prof. Okay, in this session, we have the second speakers from Malaysia, and I will read his CV. Professor Muhammad Hisham Lee. Hello, Professor. I'm Tuti, and will be your moderator today. Professor Muhammad Hisham Lee is from University Technology Malaysia. He was born in Malaysia and holds a degree in Bachelor Science in Statistics, and Master Degree too in University Kebangsaan Malaysia, and he got PhD in Mathematics in University Technology Malaysia. He has been the faculty since 1991 and currently serving as professor of the Department of Mathematics Science in University Technology Malaysia, and he is a member of the University Senate in UTM. And in this session, he will present both his research Sparse logistic regression with an adaptive penalized likelihood method for optimal variable selection in high-dimensional data classification. Please welcome Professor Muhammad Hisham Lee. Time is yours, Prof.
Assalamualaikum. Can you hear me?
Waalaikumsalam warahmatullahi wabarakatuh.
Okay. Thank you very much, Ms. Chairperson, for your kind introductions. Hope you can see the slide well. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirrabbilalamin. Wassalatu wassalam ala rasulillah wa ala alihi wa sahbihi ajma'in. Amma ba'. All praise is due to Allah alone. Have a very good afternoon to all my friends, colleges, students, ladies and gentlemen. So thank you very much for attending today's sessions. First and foremost, I would like to congratulate IPB University, especially the departments of Statistics, Faculty of Science and Natural Sciences for successfully organizing this international conference. So as we know, data utilization is a hot topic today. and also as a trendings. Researchers are working very hard to find optimal solutions and use mathematics, statistics, and also data science for a better life. So I acknowledge it takes much hard work to make this conference a successful and memorable event. Therefore, I would like to congratulate the organizer, team members for this extraordinary setup. Indeed, all participants can benefit from these events. This conference can attract more than 120 papers mentioned by Dr. Anang, Pak Anang, shows a remarkable acceptance of this conference by most researchers in mathematics, statistics, and also data science across this region. Surely this will inspire creativity and innovations, and a big congratulations again to IPB University and for a well-organized conference. So I firmly believe this is an excellent opportunity for researchers to check out the latest advancement in research areas, mathematics, statistics, and also data science, and open up opportunity for strengthened collaboration among us. It's a tremendous pleasure to meet everyone here today and meet other invited speakers in this conference. So I want to express my gratitude to Prof. Dr. Hairi Anwar and Pak Dr. Anang Kurnia for inviting me to this remarkable event. So we first met in PSU, Prince Songkla University, back in 2018, I think, when Prof. Don invited 3 of us. So I'm happy to see my dear friends here. I think Associate Professor Dr. Suhartono, I believe, is here. And also some of my friends from ITS, like I think Pak Mashuri, Pak Dedi, Harry probably is here also, I think. And also I was informed that Dr. Vinite from UNS, he messaged me that he will attend these sessions. So, today I will talk about one of the work that I have done recently with my colleges and PhD students. So the talk today is sparse logistic regression with additive penalized likelihood method for optimal variable selection in high dimension data classifications. So thank you very much for the nice poster. So recent technological advancements have made classification high dimensional features receive a strong interest in modern science study and applications. As you can see, variable selection is a common encounter problem in sparse logistic regressions. Researchers introduce regulations technique such as Lasso, SCAD, additive Lasso, etc. Have a lot of other methods. High dimensions data refer to a situation where the number of explanatory variables exceed the number of observation data in the data matrix. And we can see the example applications for high dimensional data. So in genomics, chemometrics, pattern recognitions, econometrics, some of the some of the areas that you can see the evolved data hallucinations related to high dimensionals. The next thing that I would like to mention is that for sparse logistic regression, this is an importance in many scientific research areas, as given example above. So basically, logistic regression explains the relationship between the response variables of interest and a number of explanatory variables. When dealing with these high dimensional data, we do encounter issues, especially related to multicollinearity, singularities, and so forth. So the obvious is that the column or the P or the variable is more than the individual or the row or the observations. What are the challenges? So the traditional estimation methods, for example, S basically tend to perform poorly. And we also have issue in terms of not full rank for the Hessian matrix. And other issue will pop up will be something like overfittings, estimation instability, prediction interpretations. All this is mentioned in some of the reviews. For variable selections, okay, play an vital role in sparse logistic modelings with high dimensional model. Basically, what we want to do is select only a subset of important variables. For today's talk, the research problems will be mentioned after this. So penalized method have drawbacks such as having bias and inconsistency that make the lack of oracle properties, and also encourage grouping effect in terms of robustness and so forth. And we also know that for estimations using OS and MLE, neither correct in using the initial weightage. So these are some of the issues that normally we encounter. As for the penalized estimation method like Lasso or the elastic net, basically the method is inconsistent in terms of variable selections. So large coefficient can cause the L1 norm bias because large coefficient will take more considerable penalties. So the research questions will be something like this. How to propose additive penalized method instead of existing method that I already mentioned their discrepancy. Then what we want to do is to improve the predictability accuracy. What is the significant gains that achievable when we propose a new method? So what will be the best criteria that we're going to use to evaluate the proposed method? So how can proposed additive method apply in real life? So these are some of the things that we're going to mention in this talk. And as for our aims of this research, this study aims to determine the sparse logistic regression modeling accuracy on high-dimensional data of antifungal agents. Okay, so we're going to mention that in details after that. So based on the diverse series of antimicrobial agents, we classify the agents into two groups. So this is the first. So we have the 108 active compounds, okay, and we have the inactive compound 104. So basically we have two groups there. The details can be found later. Okay. So research objective are to improve the sparse logistic regression model variable selections in adaptive penalized techniques. So a technique will be introduced to compare the proposed method with popular penalized method such as Lasso, SCAD, and also additive Lasso. The third objective is to assess the proposed method classification performance with other penalized using performance metrics such as classification accuracy, sensitivity, specificities. Penalized method, okay. Penalized method has shown to be successful in handling high dimensional data. So the trick is we have the shrinkage, okay, to impose a size constraint to the parameters. So basically we are adding an additional terms of lambda j beta. These penalized terms which depends on the positive tuning parameters d lambda. A solution to perform variable selections and model estimation in high dimensional data simultaneously. So this penalized method can do that. And a penalty terms add to the likelihood functions. Just now I already show you the equations. So basically this is to control the complexity of the model and also can improve criteria for variable selections, introduce some constraints. Just now we have already shown you the constraint. This constraint force some parameter to be exactly zero. So this shrinks the values, the coefficient to zero. the amounts of penalties terms is trade-off with the variance and bias of the selected model. So this is basically is a trade-off. The amounts of penalty terms is the trade-off between the variance and bias. So basically, if you have more smaller leads to select more explanatory variables with little bias, but with a high variance, and the opposite. So here I'm going to show you some of the penalized method. So the popular one is the rich regressions. Okay, basically it's very good if the high dimensional data have multicolorability issues, high multicolorability issues. So basically this shrinks the regression coefficient towards 0 by adding L2 norms penalty. The residual sum of square, but never equals to 0. I'm going to show you the formula after this. Okay. And we have the Lasso methods. Basically, the full name is least absolute shrinkage and selection operator, introduced by Tipsharani back in 1996. Okay, adding one norm penalty to the likelihoods. So this can perform variable selection by assigning some experimental variables coefficient to zeros. Okay, so this one definitely can go, can assign to 0, not near 0. But the shortcomings are follows. Cannot select more explanatory variables than the number of observations. Okay. Select one variable among the high correlated variables. Okay. So we have that issues also. Does not have the oracle properties. So these three is the shortcomings. We have other methods. Okay. The elastics net. Basically, the penalty is a linear combination of L1 and L2. You have a correlation base. Then other, you have like additives, Lasso penalty introduced by Zoe after 10 years, 2006. Penalty methods, okay. We have other method also. Here are the formulations for the penalized methods. So as for the L2 norm penalty, you can see the rich regressions introduced. Okay, you have that. You have the additional terms here. As for L1 norms for Lasso, so this is the formulas, and for additive Lasso, we have the weightage here. Okay, all right. So Lasso cannot select more P than N. Okay, Lasso tried to select one variables among correlated variables. So basically this is group of correlated variables. Lasso does not have the oracle properties. So with that, we try to formulate some things. So they penalize logistic regressions. So we start off with suppose X be Bernoulli random variables with parameters P. Then we have X1 until Xn be the independent random variable of X. The response variable Y, okay, has a Bernoulli distributions. So this is the distributions. Then the conditional probability of Y is equal to 1 given X. So this is the formulas, all right? And the likelihood functions of the sample is this one. So this is the likelihood functions, right? Then we have the log likelihood functions for this one. So this is the things. So next is the penalized logistic regression model is defined as this. So basically we have the additional terms here, lambda, j, beta. So lambda is the tuning parameters. Okay, lambda must be more than 0. So this j beta is a penalty functions here. So L1 penalty, penalizations of Lasso is given by this. Okay, so this is the basis. This is what Tipsorani give the formulation of J beta here. Okay, absolute value of this summation of absolute. Maximum likelihood solutions, okay, for beta, okay, Lasso is this one, right? So this is the likelihood plus these penalized terms. This is based on Lasso. So already mentioned the shortcoming. So you basically cannot select more than n variables, cannot make group selections. Equal penalty for all variables, coefficients, so make bias in variable selections, lack of oracle. So this is the shortcoming. So next is the additive Lasso introduced by Zhou 2006. So this is the formulations. So as you can see, we have the lambda, okay, have a gamma mode, then you have the beta J initial. So it's an initial estimate for each beta J estimate using Lasso techniques. Different weights are used to penalize different coefficients. Okay, so this is our proposed method. So we're going to let Wj the weight inside the L1 norm as follow, where the BWR, so this is between ratio, okay, is the ratio for every predictor variable J that is defined as shown this. So this is the formulations, okay. Basically, it gives you the ratio of between and betweens. So this one is denote the average of column J across row, and this is denote the average column J across column belongings to class K. All right. This is the computational algorithms. Okay, this is a step. Okay, as you can see. Okay, it's similar like previous formulas. The proposed method. Okay, so the name that we put here is the additive penalized logistic regressions. Okay, APLR equation has a convex forms, which ensure a global maximum point and can be efficiently solved. Okay, the coordinate descent method can be used to solve this APLR. This is our data sets. So the data set is a diverse series of antimicrobial agents with respect to bioactivity agents. Okay, so this is the Candida albicans. So I'm luckily that I work with some college and also lecturer from departments of chemistries. So they do have these data, and we works and we managed to publish several papers related to these anti-agents fungals. So the data, this is the data. Okay, basically you have 10 of these components, you have 9 of these components, and so forth. Right. So in terms of performance evaluations, okay, we're going to use these 3, whereby it's quite standards. Okay, we have the classification accuracy, sensitivity, and specificity. Okay, so these all 3 is denote the true positive, false positive, and so forth. So the higher the value of the use evaluation criteria, the better classification performance is. So the higher value of, okay, right. Experimental setup. So this is a setup. So the experimenter randomly split the descriptor molecule into 2 partitions. So we're going to have a trainings 70%, and we're going to have testings, okay, data sets 30%. So this is for cross-validation purpose. So the experiment used 10-fold cross-validations and average 100 partition times. Okay, the tuning parameter value is between this. Okay, 0 to 100 depends on the training set. Okay, and also the experiment set the constant A to 3.5 as for the SCAD penalties. So this is mentioned in these articles. Okay, this is our experimental results. Okay, so table 1 show you the training data set performance evaluations of penalty techniques. Okay, so this is the proposed method. Okay, this is a 3 compare. This is the number of descriptor that we managed to get from the data. Then we have the CA, and also specificities. Okay, this is the classification accuracy. So from here we can see that the value, this is higher compared to the rest. This one also is higher, and this also is higher compared to the rest. So the additive penalized logistic regression method provide a lower number of descriptor. So the APLR method able to provide better accuracy in terms of classifications, as you can see from here. So for table 2, so the test data set performs value penalty techniques. Okay. So this, as you can see, that this is the proposed. So this is the value. Okay, is larger than the rest. Okay. So able to provide better accuracies in the classifications, right? Next is this one. We also do a comparisons of pair t-test for classifications accuracy. So we're going to look at the CA only in terms of that. So we compare the methods, our methods, the APLR with these 3 methods. Okay. This is Lasso, sorry. Okay, so if we do the comparisons, so it shows that this is the p-value, a significant difference, okay, from the proposed methods. Okay, in terms of classification accuracies. In sorry, this is in trainings. This is in testings. Okay, I will correct it later. So this is a testing. So this is a statistical significance difference between the proposed method and other method at the 5% significant level. So in conclusions, so this study aims to determine the sparse logistic regression modeling's accuracies on the high dimensional data of antifungal agents. So we improve the sparse logistic regression models, variable selection with an additive penalized technique based on the diverse series of antimicro agents. We compare the proposed method with a popular penalized method such as this. The improved were distinct and consistent through the pairwise t-test, as mentioned before this. So the experimental results show the superiority of the proposed method over other methods, okay, especially in the number of selected descriptor and classification accuracy. For further details, okay, you can have a look at these articles published this year, okay. So all the details, it will be available here. And as also some related publications to high dimensional data that we work out. This is the 5 years, okay, the recent 5 years publications. So some are quite latest. You can have a look of these publications. And if you need a copy, just inform me. So I'm pleased to provide a copy to you.
Thank you, Prof.
Okay, going to finish. The last slide. Yeah, just email me, and inshallah I will provide the articles if needed. So this is my research teams related to high dimensional data. Prof. Zakaria Yahya Agama, he's my ex-students. Now he's already professor. And we have Dr. Abdul. Okay, he's from chemistries, and have another Prof. Maslan also from chemistry departments. So basically, if you're dealing with data that are related to chemicals, so they will be involved in terms of interpretations and providing the data. And we have Dr. Yusrina also, and also Dr. Ain. This is my latest students doing in these fields. Yeah. With that, I would like to thanks IPB University for inviting me to this conference, and thank you very much for your kind attentions. Thank you. Wabillahi taufiq. Wassalamualaikum warahmatullahi wabarakatuh. Back to you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof. Muhammad Hishamli. This is great presentation, yeah. And maybe we will go to the next session, yeah, Prof. In Q&A session about maybe we have more time, yeah, about 15 minutes. And there are one question, yeah, from Bapak Raden Aurelius Andika Viadi Nugroho. Okay, this question is for Prof. Ken. Hello, Prof. Ken.
Hi.
Okay, maybe please, Bapak Raden Aurelius, open your video and your audio. Halo Bapak Raden, are you there? Okay, maybe I will read his question, yeah, Prof. The first question is, can we implement this model for multimodal data, example involving crop field image data and others? And maybe first question, yeah. Okay, Prof.
A quick question. Well, a quick answer is I don't know.
Don't know. Okay.
All right. Okay. Definitely dealing with multimodal data is going to be very complicated, very challenging, because by nature is a multimodal, right? Okay. So I do not know whether our proposed model, work in this setting. All right.
Okay. And there are next question, Prof. How do you pre-process the data if there exists missing data in some data?
Well, missing data is definitely a big issue in our line of work. So certainly there are a number of statistical methods that you can apply. For example, the standard method like the imputation. So I presume that you can apply to using technique like that. But in our work, because we use the data from the United States, we have the luxury that the data is actually quite complete. And we at least in this particular application, we don't have to worry about the missing data.
Okay, that's great, Prof. Okay, sorry, Prof. I will read again, yeah, Prof. The third question.
Okay.
PCA are known to have some weakness when the variables are so many. The factors that produce from the PCA may not explain that data enough. Is there any alternative that you can suggest for reducing the data dimension on the analysis that you conduct?
Okay, so certainly whenever we're dealing with a high dimensional data, it's going to be very challenging. There's not going to be a one model fits all possibility. Otherwise we don't have to do any more research. Okay, right? Okay, is a challenging issue, and that's why in our model, which I didn't go into details, is that when our very first step, we actually use the PCA to identify the key component or the important factor. But after that, we proceed to the second step in a supervised manner to then, out of these principal components, we in turn determine what would be a even better, smaller subset using a different criteria and so on. So hopefully that, through this process or through this additional supervised step, we can produce an additional dimension reduction and can achieve better crop yield prediction. And again, in terms of the other alternative, like like Lasso, this the topic previous speaker talked about could be a potential potential is a potential. And again, I would suggest that this researcher to do a Google search on high dimensional PCA. There are actually a lot of paper has been published in addressing the problem with high dimension PCA, and what are the ways that you could address this issue, when it comes to high dimension. All right.
Okay, thank you, Prof. This is great information, Prof. And I hope Mr. Raden already heard that, yeah? Okay. And then for the next question is for Professor Hisham Lee. Okay, this is for your. Okay, I will read or Ibu Rahmanisa. Okay, please Ibu Rahmanisa to open your audio. Okay. She want me to read that. Okay. Professor Hizamli, the question is, what are the particular characteristics of the data set or any other consideration that drive you an idea to use the proposed method? Okay, please, Professor Hishamli.
Yeah, thank you very much. Indeed, it's a good questions. So it's very important to identify the correct data sets, especially related to high dimensional. The first characteristics that we can consider and will be very important will be these the numbers of p must greater than n's. In my talk, I already give several examples. For example, in genomics, okay, chemometrics and pattern recognitions. These are few that normally people will encounter that actually you're going to have a characteristic that p variables are almost most of the time will be greater than the observations that ends. So this is one of the important criteria that you should look into. Then next, when you come to the situations whereby you like to do logistic regressions, whereby the classification is very important. Here, the creativities will kick in. For example, in our study, you can see that I mentioned the data is have a diversities in terms of the values. So happily that the data actually can be classified into two groups, okay, whereby we use the medians as our cutting points. So and we discuss with our counterparts from chemicals departments. So basically, they also say this is something that actually is good to look into. So this is something that important for us to encounters. By the statisticians know what is the characteristics for the logistic regressions, and for the applied people whether this is something that beneficial or not to them. So this kind of mesh and collaboration is very important. So then we can make the data utilization a beneficial ones. So hope answer the questions. Thank you.
Okay, thank you, Prof. This is great answer, Prof. Okay, maybe are there any question from the participants? Please raise your hand if you want to ask. We have about 5 minutes later to close the session, and we still have time to Q&A session. Okay, are there any participants to raise hand?
May I ask directly? My name is Suartono.
Thank you, Prof. Sartono.
Okay, I will ask to Prof. Ken Seng Tan. Thank you for the opportunity. Yeah, you explained about the principal component analysis. And we know now that there is a new progress in principal component analysis, especially for the nonlinear one. Recently, most people deal with nonlinear problem. And for example, people who learn about neural network or other machine learning approach, they propose about the principal component analysis for nonlinear relationship. How about Prof. Ken opinion with the principal component analysis for nonlinear relationship in your cases? Thank you, Prof. Ken.
Again, definitely welcome to, this is part of research, right? Okay. Unless you know more about the data, some of the characteristics, so we can do more. And definitely I welcome research in this area, try to continue pushing the boundary, right? Okay, so again, like, statistic without any empirical study, it would be rather difficult to know whether that will work or not working, right? Okay, but definitely these are hot area, and welcome, continue doing research in this direction. Okay, right? Okay.
Thank you, Prof.
Okay, thank you, Pak Hartono. Okay, maybe there are any participant want to ask? Please just open the video and audio. Okay. Okay, maybe there are no question again. Maybe we have to close this session. Yeah, please, all participants giving applause to our speakers today. Thank you very much, Prof. Ken and Prof. Hisham Lee. And this is great presentation, yeah, from Prof. Ken. We already learned about improve index insurance design and yield estimation using dynamic factor forecasting approach. And from Muhammad Hisham Lee, we have learned about sparse logistic regression with an adaptive penalized likelihood method for optional variable selection in high dimensional data classification. And now we are about to close our plenary session. We got so many knowledge and new insight from each speakers today. Thank you so much for great presentation from our speakers and also for our audience for the enthusiasm following this plenary session. And I'm Tuti and I'm very happy to be your moderator today. Please giving applause for our plenary session. See you again in the future moments. Bye-bye.
Thank you.
Thank you. Assalamualaikum.
Okay, time is for Ibu Sarah. Silakan.
Thank you. Ibu Tuti already lead the panel session 2 on this ICMSDS 2020. And again, big word of thanks to both of you, distinguished professor, Professor Ken Seng Tan from Nanyang Technology University of Singapore, and to you, Professor Muhammad Hisham Lee from University Technology of Malaysia for your sharing this afternoon. Ladies and gentlemen, I'm sure you will agree with me that it has truly been an honorable virtual tour to meet and learn from so many bright minds from many cities and countries from all kinds of backgrounds and expertise. We now invite Secretary to the Department of Statistics, IPB University, to deliver the certificates of appreciation to the both of the invited speakers, either to the moderator. We welcome you, Dr. Bagus Sartono.
Okay, thank you very much, Ms. Sarah. Good afternoon, everybody. Assalamualaikum warahmatullahi wabarakatuh. On behalf of the committee, we would like to thank Pak Suhartono as the Indonesian Forum of Higher Education Statistics to join this conference. Of course, we would like to thank to Professor Ken Seng Tan from Nanyang Technology University and Professor Muhammad Hisham Lee from the University Technology Malaysia for a very nice talk, very inspiring. I think all of us grab a lot of knowledge from both of you. As an appreciation for us, please, we would like to share you a token of appreciation. We apologize, it's very simple appreciation and digital. For committee, please share the token appreciation. And we hope that you impressed with this token. Thank you again, Professor Keng Seng Tan from Nanyang Technological University, Singapore.
Oh, I look
and
much
also
younger.
thank. I hope you're happy with this
Very nice.
picture.
Thank you very much.
And also for Professor Muhammad Hisham Lee, please. Okay. Professor Isamli.
MashaAllah, very nice.
This is, thank you very much again.
Yeah. I hope you can send a soft copy to me.
Yes, yes. We share
Nice.
to both of you. And of course, we also like to thank to Ibu Tuti for a very nice chairing the plenary session today.
Thank you to Prof. Bagus.
And hopefully, after the pandemic of COVID-19, we can gather in the other conference in person. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you.
Thank you.
Thank you to all of you distinguished persons. Distinguished guests, ladies and gentlemen, we are now come to the parallel session 2. Still, there will be 6 topics to discuss in the 6 different rooms. Again, kindly rename your ID name on your each screen using format room underscore session and underscore name. For example, as we now will come to session 2, and we will discuss in the room A, and my name is Sarah, then I will write A underscore 2 underscore Sarah. Or if you are the presenter, so you can rename your ID using format A underscore 2 underscore presenter underscore bunga. The parallel session 2 will divide it into 6 rooms. Room A will discuss about small area estimation and will lead by Ms. Rizky Haryastuti. Room B will discuss under the subject structural equation model. This session will lead by Ms. Marta Sundari. Room C will discuss about classification and will lead by Ms. Anggita Rizky. Room D will discuss under the subject generalized linear model, and the chairperson will be Ms. Meli Amelia. Room E will discuss under the topic time series, and Mr. Doni Citra Lesmana will lead in this room. And room F will discuss other subject. Mr. Bib Paruhum will lead on this room. But before you go to your each room, ladies and gentlemen, allow me to deliver one point as the program announcement. Tomorrow, we will continue our conference as the second day as well as the closing day of ICMSDS 2020. By 8 in the morning at Jakarta time, we will have panel session 3 and continue by parallel session 3 and panel session 4. In the afternoon, the agenda are panel session 5 and the closing ceremony. Make sure that you will attend the closing ceremony because there will be the announcement for the best paper, best presenter, best audience, and maybe another best for you. Thank you very much, ladies and gentlemen, for your attention. Enjoy the rest of the conference.